Righty, looks like it's 1 o'clock, so we can get started here. Today is the gamma ray detection lecture by Ricardo Lopez. Ricardo is are you in your third or your fourth year of your PhD? Third?
Just started third this summer, yeah.
Third year of his PhD, and he is a student in Dr. Sarah Pozzi's lab. Ricardo works in particular in neutron detection, and we are very excited to have him here today to give the discussion. So if you have questions, please put them in the Q&A. We will answer them at the end. If you have any questions, just put them there. Anyway, without further ado, Ricardo Lopez.
Yeah, thanks, Peter. So as he mentioned, everyone, unlike for those of you that were here yesterday, for this one, we'll do all the questions at the very end, and then we'll have a nice Q&A session so folks could ask our questions as we go along, but I won't quite stop as I go through this. We can do that at the very end. So also as mentioned, so my particular focus with my research is specifically with particle imaging. And although in a couple of lectures from now, I'll be giving another talk on specifically particle imaging systems. Today, though, we'll actually be focusing simply on gamma ray detection, what that entails, and then we'll have some cool discussions on the applications for that. So I'll just start off with by going through a bit of an overview of what we'll be covering during today's talk. Specifically, I'll just begin with just giving some context on processes for gamma ray detection, and then some of the applications that those particular processes help us with. Then I'll proceed with the actual detector types, and then classify them based on certain aspects for those systems. And then finally, we'll wrap this up by going through some specific examples, particularly here, I'm gonna go through some gaseous detectors and some solid state detectors. So look forward to that. But before all that, I'll start at the very beginning. And indeed, in the very beginning, there was nothing. And if you were to ask the Greeks, you basically have the sky and the earth. In this case, we have Oranos and Gaia. And of course, with that, we also have the underworld. And now you may be asking, why am I starting this particular lecture with this? Trust me, there's a point to this. It'll all make sense at the very end. But for now, there's also a neat thing that we can discuss, which is, well, where did some of the elements actually get their name? Specifically, with regards to nuclear safeguards, one particular element of note is uranium. And as you can imagine, if you ever did imagine, where did uranium come from? Its name came from, the planet Uranus, but where did Uranus come from? Where did that name come from? It was from the god Oranos, which was from Greek and Roman mythology, just in case you were curious. Speaking of Greek mythology and the naming of elements, there was another one that's another element that's also very special for nuclear safeguards that also has this kind of quality, which if we just talked about the underworld, we have the god of the underworld, Hades, or if you were Roman, you'd say Pluto. And what you'd actually tend to see is that with the exception of the other planet, Uranus, the other planets actually got their names from the Roman version of the Greek gods, or rather they were using their Roman names, which is why we ended up with, in this case, plutonium for the ultimate name for that particular element. So just A, some neat trivia, B, like I said, we'll wrap this up at the very end. I'm closing this particular lecture with the Greeks again. So keep that in mind for later during today's lecture. But onto the actual discussion on the science. So as mentioned, today we'll be talking about gamma ray detection. And I'll start off by going through some of the applications before we even start talking about, how are gamma rays detected? What kind of systems do we employ? I want to begin by first talking about, where are said systems used, for what kind of scenarios would they be used for, and why? So one of the first ones I like to discuss is accident scenarios, specifically for nuclear-related accident situations. As you can imagine, during some emergencies, take Chernobyl as for a historical example, when you have that kind of incident and you have a release of radioactive material in a particular environment, it's really important to A, figure out, is there material present in a particular, area of like a particular region? And if so, what is it and how much of it is there, or rather like how much activity, how much dose would a, person standing within that general region expect to receive? And as you can imagine, under that kind of situation, gamma ray detection is very important because it's by which the means that one is able to actually map the area, determine what regions are safe, which regions are not, and ultimately be able to pinpoint, what kind of contamination are we dealing with. You can get the information of the isotopics, and once you have that kind of information, you can pass that along, the line of command, and then be decided, how should this accident scenario be approached? What precautionary measures should be taken to protect, everyone involved in that particular situation. Another one, which is actually very closely linked to the accident scenario one, would be source localization. Now, localizing a source in general is very important for a lot of different fields. The most straightforward one would be, say, in a search and rescue scenario where a source has gone missing and has to be located very quickly. One very recent example was the one medical source that was lost over in Australia a couple months ago, I think at this point. So that would be an example of where you have a missing source, or that there's a source present in some search area, and you need to be able to actually localize and find it to a certain extent. And again, there's one application where gamma ray detectors would be very useful, because oftentimes the radiation sources in question are typically purely gamma emitting, or have a very significant gamma signature that would be relatively easy to find using the correct kind of system. Another application would be for environmental monitoring. And this has a lot of different aspects related to it, actually. You can either have it for, in general, monitoring that a particular environment stays relatively clean with regards to like radiation, especially radioactive waste. One common, place where you would kind of find this employed would be near reprocessing sites or other facilities that process and work with radioactive material. You want to make sure that nothing accidentally makes it out to the environment that shouldn't find its way over there. So that would be one example where, if there is a accidental leak or dispersion of material, it would be effectively monitored using this kind of system, which oftentimes will end up relying on, say, any of the gamma ray signatures from those particular sources. Another really popular, application of environmental monitoring also pertains to the monitoring of nuclear weapon explosions and testing. So, as some of you may or may not know, there's an international agreement. It's called the Comprehensive Test Ban Treaty, that's signed by various nations that all are in agreement that they will not be performing, live weapons testing, and it's since then been adhered to for the most part for parties. But of course, there are some states or state actors that aren't necessarily part of that treaty, so they don't actually follow it and do, actually perform weapons testings. One prime example would be, for example, North Korea and their weapon testing, weapons program, and the subsequent testing. So there's a large series of small measurement stations located, dotted around, around the world, that are used basically 24/7 to monitor like background levels of certain kind of radioisotopes. And once, a spike is observed for a certain type, for example, one of the popular ones would be radio xenon. So during the nuclear explosion process, some radioactive isotope of xenon is produced that, no matter what you do, it's going to find its way into the atmosphere. Even if you do the testing underground, it'll end up seeping through the ground and make it into the atmosphere, which could then be measured by said environmental monitoring systems that are dotted around the world. And if you see that kind of spike across various of your systems, then that would be an indication that, oh, someone's probably performed a test right now, and now it's the job of the international community essentially to figure out who's responsible and what was actually done in terms of what kind of weapon was used, what material was used within that system, et cetera, et cetera. So again, another very important application with regards to the nuclear safeguards regime. And of course, last but not least, another very popular application for radiation detection systems is for the characterization of sources, specifically for treaty verifications within the general nuclear safeguards regime that is established between certain nations in the world. The governing body in this case would be the IAEA, or the International Atomic Energy Agency. The International Atomic Energy Agency. Sorry, sometimes I get that mixed up. But essentially what they're charged with is sending their inspectors out onto the field and verifying that certain treaty obligations are being met. And oftentimes what that means is simply confirming the presence of specific radioactive materials and confirming that it's of the declared composition. And as we'll see, being able to take the gamma ray spectrum of certain samples will definitely give you the kind of information that you would require to make that kind of call or make that judgment in terms of whether or not what's being declared is actually what's present in front of you with your system. And of course, I just want to note that not all the applications are inherently nuclear focused. There's definitely a lot of other applications for gamma rays that doesn't have to be revolving around nuclear. One example would be with regards to medicine. I know we talked about this yesterday, where there's certain applications, particularly with a lot of surgeries and other procedures, but radiotherapy and medical imaging are among like the most common forms where you'll see a lot of gamma ray detection systems being employed nowadays. And also astrology and just the study of space. We use a lot of these high energy gamma ray events that are produced in these kind of far off events in space or in our universe that can tell us a lot about how certain, phenomena are occurring in, regions of space that we do not have access to, right? Because they're just so far away. But because gamma rays essentially travel at the speed of light, eventually they hit the Earth, and we're able to collect them and to learn some information. So I'll start with now going through the actual processes in which we actually perform radiation detection. As we talked yesterday, there's essentially two categories of radiation that we're concerned with. Essentially, we have the directly ionizing types of radiation, which the common aspect between all these is that they're charged particles. So we have alpha particles, beta particles, and other heavy ions. But then on the other hand, with the other category, we have uncharged particles, or uncharged particles, that being neutrons and gamma rays / X-rays, or photons, if you will. And we call these indirectly ionizing because while neutrons and gamma rays won't directly cause the ionization, they can lead to certain mechanisms that then indirectly lead to ionization in matter. So this being with a lot of nuclear reactions with neutrons and various mechanisms with the gamma rays, where via these mechanisms, you end up with charged particles, and this more oftentimes they'd be protons, recoil protons, or recoil electrons, which then actually do the ionization and either create something like electron ion pairs or electron hole pairs if it's a solid or gas, or really it depends on the type of detector that you're working with. But we'll get into that in more detail as the slides go on. But just as a note that yes, directly speaking, we're not measuring the neutrons and gamma rays always directly. Sometimes we have to go about it in a roundabout kind of way in order to actually confirm their presence in certain systems. Now, as for the photon interactions of matter, there are quite a lot of interaction types that you can come across with gamma rays. There was a couple that we mentioned yesterday, but just really quick as a speed run, if you will. We have the Rayleigh elastic scattering, Thomson elastic scattering, photoexcitation, and then the big three, which are highlighted in red here. They're the most important when it comes to radiation detection, because more often than not, it's one of these three that is actually being used by a lot of the common gamma ray detectors that you end up either seeing in the field or in labs. And so these being the photoelectric effect, the Compton scattering, or pair production. And while all the other ones that aren't highlighted in red are indeed noteworthy and have like their own very specific uses for very specific applications or fields, just for the purpose of keeping this particular lecture fairly general, we'll just focus on these big three for now in terms of discussion with radiation detections. Also, something that we talked about briefly yesterday was this idea of the cross-section. And the best way that you can think about this, for those of you that haven't studied this or aren't really familiar with the cross-section, is you can just think about it as essentially the likelihood or probability that a certain type of reaction occurs. In this case, the big three that we talked about being the photoelectric, the Compton scattering, and the pair production. The way that the relationship between these three is that as you go higher in energy and higher in Z, or rather the proton number of your particular atom that is being included in the interaction, then the more likely pair production dominates. When you're at very high Z and also very low energy, then that's where photoelectric effect tends to dominate. And then you have this region in the middle where across a broad range of Z values, and then within, say, 100 keV to 10 MeV, that's where you have gamma ray Compton scattering being dominant in this case. And to give you an idea of, here's a plot of the actual cross sections, particularly this case is with respect to lead. And here we have the blue plot representing the total. If you were to sum all three cross sections, this is the distribution that you get. However, we can actually break it down into the individual different interactions, where this red dashed line is the cross section for the Compton scattering interaction. The aquamarine color is the pair production, and the photoelectric is in green with dots. So there's a couple things that are noteworthy that we can here discuss. The first being that the Compton here, the Compton probability, if you will, is fairly not, I wouldn't say constant, because it's important to note that this plot right now is in log, so it's logarithmic. So even though it seems fairly smooth, there is a higher probability towards the aforementioned energy range from the plot that you see over on the left. However, you can generally see that it's fairly well behaved, and it's fairly consistent in terms of a broader energy range. That isn't the same though for the other two, photoelectric and pair production. For the photoelectric, you see just how astronomically higher it is at the much lower energies. And you can also make out these kind of jagged features in the plot. These actually just have to do with specifically the electron binding energy. So as you have electrons at different shells or orbitals, the amount of energy it takes to actually dislocate them from their particular spot in that energy state is very much dependent on which level they actually happen to be at. And that's what these jagged lines are actually representing. And then finally, with their pair production, you can very clearly see that it's for all intents and purposes non-existent prior to a certain threshold value. And as we talked about it yesterday, the threshold value happens to be 1.022 MeV, which is twice the Rust mass energy of an electron. Since during pair production, we have to essentially create the two the particle and antiparticle pairs, which means we at the very least, at a minimum, there's some Rust mass energy, which is why the pair production cross-section really only happens starting that threshold. And then very quickly, as you go in higher and higher energy, it starts to become the dominant one. Since the more amount of energy you have, the more can actually be contributed to this pair production process. Now, I'll also note that the whole positron and electron creation isn't technically the only particles that can be created during this process. As you go to much and much higher energies, larger particle and antiparticle pairs could end up being produced. It's honestly just very energy dependent. But typically for in the lab and for a lot of the radiation sources that are of interest to us for measurements, for verifications, and they're often dealt with in industry, it's typically just the electron and positron pair that we'll be seeing here, though, because that's roughly the most likely one to happen or that's the one that's most allowed in the particular energy ranges that we're dealing with. So now that we've talked a bit about the actual mechanisms, what about the actual detectors that are used? And so one can classify these detectors into a bunch of various categories. So we have the ionization detectors, which happen to be some of the earliest ones and also some of the simplest ones to construct. And because of their simplicity, they end up being the ones that are most commonly used, since they tend to be fairly cheap to use and out in the field and equip people with. And so that will be the first bit that we talk about. However, there's also a lot of other types of detectors, such as luminescent ones, scintillator detectors, which will be essentially the other big focus of this talk. As I mentioned at the very beginning, my focus in research is with particle imaging, and I perform that particle imaging with these type of scintillation detectors. So if there's any questions when we get, or at the end of this talk, any questions specifically related to scintillators, I'd be more than happy to cover that if I don't already cover that in some of the following slides that we'll be going over. And then, of course, we have semiconductors. These are also another very prominent detector type. One of the popular ones in research right now. You have any super specific questions regarding that, you can also ask Peter's here, and he is fairly knowledgeable with regards to those, since that's more in line with his particular work. And then, of course, finally, we have chemical detectors, which are a lot of these photographic emulsions or films, which you recall were historically how a lot of these particles and generals were originally found or discovered. It was using these kind of photographic films in order to actually note that, there's actually something here that we just can't see with our naked eye. So as I mentioned, I'll start by just going over ionization detectors. And I will note that there's going to be a neat upcoming lecture. The one following mine will be on alternative semiconductor materials rather than just traditional ones. So again, if it is something that you're really interested in, look forward to the next lecture on that. We're going to have a guest speaker talking a bit more detail on that particular topic. So we'll start with talking on gaseous ionization detectors. One of the very common ones that would be used, or rather that would fall under this category, and they're kind of popular within the general public, would be cloud chambers. And there's a very popular kind of demonstration, especially in a lot of middle school or high school science labs, which would be you can very easily just make a little chamber or cloud chamber and then place a radioactive sample in the middle, and then you can see visually with your eyes some of the tracks that some of the particles are leaving behind. And for this particular little video here that's looping on the slide, this is just a small piece of uranium ore. And what you're actually seeing coming off it are the tracks from the alpha decay with this particular source. So the way, very brief overview on how this cloud chamber actually works is you enclose this particular space with very saturated vapor. It could be water, but more often than not, it tends to be alcohol, since it tends to give a lot better tracks. And you essentially have very super saturated vapors within this enclosed space, a metal plate, and then some cooling below. And as particular ionizing particles travel through this super saturated environment, they basically ionize some of the molecules in the vapor, which end up serving as nucleation sites for very, very small water droplets. And that's why you end up seeing these kind of vapor or misty kind of tracks over on the right. That's the alpha particles, which are a very highly ionized or charged particle that's traveling through this particular environment, and thus allowing for these high density linear tracks of nucleation site to essentially where all the water, microscopic water droplets end up condensing, and thus allowing us to see the alpha tracks. So there's a pretty neat demonstration to show that, with your eyes, you can't really see, for example, this alpha radiation, but you can very easily make them apparent under certain circumstances, in this case, the cloud chamber. Now, here's a pretty famous depiction of a cloud chamber, specifically showing pair production. And the way you would visualize this is you have a incoming gamma ray, which then interacts with one of the atoms that happens to be within this particular volume. And via pair production, it produces an electron and positron. What you can't see with your eyes is, a magnetic field is being produced perpendicular to this plane. So because of that, the electron and positron end up spiraling, following along that magnetic field lines, and ultimately annihilating at the conclusion of their path once they've slowed down. But for this particular case, we have pair production in addition to one of the electrons from the original atom in the space. One of its electrons gets recoiled, which is also then why you see this track here corresponding to the recoil electron. Of course, this doesn't always happen. Sometimes you just have the pair production, which is happening over to the track here, over here to the right, where you have an incoming gamma ray, undergoes pair production, and you simply just have the creation of the two different particle and antiparticle pairs. In this case, they have a lot more energy, so they don't immediately start curling towards annihilation. They fly off in their own directions for a bit, but you can start seeing that eventually they are affected by the magnetic field. They do start curving, and eventually will end up, well, definitely the positron here will eventually end up annihilating. But here's just a visualization of pair production actually happening, and a visual representation using with the assistance of a cloud chamber in this case. In this case, it was the nucleus that recoiled, and since it's not necessarily charged under these circumstances, that's why you don't have this kind of third track anymore, like you did with the recoil electron. So another very popular kind of gamma detector would be the ion chamber. And in principle, it's a gas-filled space where you have two electrodes at either end that are supporting an electric field between the two. So you have the anode and the cathode and some kind of voltage source. Now, as the gamma ray goes in and interacts with the gas molecules, this creates charged particles, and these charged particles are what go and travel through the gas and create these electron ion pairs. And since it's under a magnetic field, these migrate to the ends, or here you have the anode and the cathode depicting that. And as you collect the charge, you can get a signal, which then corresponds to, the fact that an event just occurred. Thus, you've been able to detect that initial incident gamma ray under this circumstance. And when you operate an ion chamber, it's actually really important what voltage you're applying between your two plates. You can operate under a lot of various regions, we call it, depending on the actual applied voltage, where if you look over to the plot here, the x-axis represents the applied voltage, and then the y-axis represents how much charge you collect for a particular event. So we see that in this first region, it's called the recombination region, because essentially there's not enough applied voltage to completely separate the charge. So some of those electron ion pairs end up recombining. You don't end up collecting that charge. Thus, you end up with a significantly reduced charge signal, if any at all, depending on how much voltage you actually applied. So generally, this region isn't used for ion chambers when they're actually used in the field. However, the next region here we call the ion chamber region is, and it is a sufficient applied voltage such that there isn't a recombination and you are actually getting the full charge during that exchange. One of the common applications that uses this particular region would be dosimetry. And then as you go further along and apply even more voltage, then you end up with this proportional counting region where, depending on how much energy was deposited, the charge changes accordingly, and it's proportional. So you get more charge as a larger amount of ionization occurred, and thus that gives you a good sense in making sure that your counting is all great and consistent. If you go even higher, you start getting to limited proportionality region, which some fields use them, some others don't, because this whole non-proportionality issue could be a problem depending on your particular application. And then finally, towards the higher extreme of voltages, you have the Geiger region, where now whenever a ionization event occurs, it basically just avalanches and fills everything, or rather it just explodes into just having a large signal, such that even a single event just fires off the entire ion chamber, and you get the same signature, or you get a single count. You don't really get any kind of energy information anymore, because even a low energy event versus a high energy gamma event would still basically produce an avalanche, and you end up just with the fact that a count happened, but you're not really able to gather any more kind of energy information from that. You can just say, yes, we got one count in this particular time frame. So a bit more about the Geiger-Müller region. So it's really popular, in fact, to the point that it basically has its own specific gamma ray detector associated with that, called the Geiger-Müller counter, as the name suggests. And in the field, primarily it's the electrons that are inducing the secondary ionization of the gas, and that's what ends up ultimately ending up collected into this kind of central anode wire under this kind of geometry. Usually this would be like in small tubes that are pressurized and gas filled with a particular gas, and then you would be using this kind of apparatus simply to get counts. This won't necessarily tell you, what kind of radiation particle initiated the event. You just know that you had an ionization event occurred to begin with. And now, because of this avalanching effect, the multiplication is just huge. So even if you get a fairly weak signal, if it does end up causing an avalanche to occur, it's fine. It just multiplies it out until to the point where it really gets out of control, and you just get a very strong count at that point. So here's an example of a Geiger-Müller counter, and I hope the sound is coming along. This is just an example of an audio file of what one would typically sound like. It's very popular in just a lot of pop culture. It's used a lot in association with just radiation. And because it's so commonplace, you can essentially buy these off, just Amazon and everything. They're fairly cheap to produce. They're very simple systems compared to some of the more complex detectors that we'll be talking about in a couple slides. but because of their ease of use and everything, they're fairly easy to get a hold of and just play around with. Cool. So next up, the other category of detectors I'll be talking about are scintillator detectors. And here, as mentioned before, so there's actually within scintillators, we classify them into two different categories. We have organic scintillators and inorganic scintillators. Now, with the first category, the scintillation light comes from the molecular electrons, or more specifically, the carbon-hydrogen bonds. Important thing to note with organic scintillators is typically they're mainly composed of simply carbon and hydrogen, which is ultimately why they have a low density and low Z in general. Now, there's a problem for some particular applications. One of them technically being with gamma rays, because they're so low Z and low density. A lot of gamma rays could end up just passing through them, but you tend to end up still getting them to interact via the Compton effect anyways, and we'll talk a bit about that in a second. But the other category are inorganic scintillators, which their scintillation light comes from free electrons within this crystal lattice that you get from the incorporation of inorganic compounds. And because of these compounds, these type of scintillators tend to be of higher density and as such be of higher Z and are a lot more efficient at gamma ray detection. Also, I guess I should mention this now for those of you that aren't familiar. A scintillator is essentially a type of detector, or more specifically, a type of material that in response to having an interaction with a radiation, in this case, let's say gamma rays, the way it responds is by essentially having one of the molecules within the actual volume get to an excited state. And as it de-excites, it emits photons or light, and then you can collect this light with photosensors, and depending on how much energy was deposited in that particular event, corresponds to how much light is collected, specifically with gammas. The principle for a scintillator detector is that you have the actual scintillator detector volume or crystal, and you couple that to, as I mentioned before, a photodetector. So something that could take those photons from the ionizing radiation and create a signal. And this, as like I mentioned before, here with a little demonstration on the right, we have the incoming radiation signified as this pink arrow at the very top, where it hits some molecule in the scintillator. Photons are a result of that, and eventually they make their way down over to this PMT, or photomultiplier tube. And the way this piece of equipment works is that there's small diodes here on this tube that the initial photons get converted into photoelectrons, and then these electrons get multiplied as they make their way through this system of diodes, and eventually you have a large enough signal that you can collect and then either digitize into a waveform, and then you can do some post-processing work on that, or you can just integrate out to get the area under this pulse to get a total signal or response for that particular event. So I can get it. If there's any questions regarding specifically the processes for scintillation, I can get into a bit more detail on the physics if that's of interest for anyone, but otherwise for now, I'll just keep it very high level in terms of there's energy deposition within the scintillator, there's excitation as a result, and then subsequent de-excitation via luminescence or the emission of photons. With inorganic scintillators, the basic idea is still the same. However, as I mentioned before, the behavior is determined by these electrons in this crystal lattice, and eventually what this ends up meaning is that you have this following this kind of band gap model, where the ionization radiation will create electron hole pairs within these material, And that's what's actually collected and used for the actual signals. Now, it's a very common thing to actually not just have, your pure scintillator. Oftentimes, because of the way that the physics work out, it's actually advantageous to include a impurity in your material intentionally. And instead of calling this an impurity, though, we would call it an activator. What it does is essentially it creates these kind of like intermediate levels within the band gap, such that it allows for de-excitations and photon emissions or scintillation emissions that would otherwise not really happen. However, there's some issues with that in terms of this general manufacturing process could end up leaving electron traps, is what we would call this, which results in delayed light responses, which could ultimately lead to what we would refer to as afterglow, which could be something that's very not desirable for certain systems or applications. And to give you an example of this kind of like activator or impurity example, so sodium iodide is a very popular inorganic scintillator, and oftentimes in literature you would see it as sodium iodide parentheses TL. That's because the thallium was used as the impurity, or rather it was used as the doped in small amounts within that sodium iodide lattice. So very common, you'll kind of see this. That's actually what it means. It's not necessarily pure sodium iodide, it has some thallium dope in it. So with regards now to inorganic scintillators, I can go into them a bit more detail in general. To give you an example of some very popular ones here on this particular slide, I have some listed and the subsequent examples of finished samples that are encapsulated. So like I mentioned before, one of the very popular ones is this thallium doped sodium iodide. Now, depending on the composition, that very significantly affects some of its scintillation properties. Depending on your focus or your application, some scintillation properties matter more than others, but some of the more popular ones are like, what is the decay time for the scintillation light to go through, the entire scintillation process? How long does it actually take that particular crystal to go? And also how efficient is your particular detector at a particular energy range? Since for some applications, you really want to be highly efficient at a particular gamma ray energy region. Now, I mentioned before that in general, inorganic scintillators tend to be of higher density. As such, they have high Z. So they tend to, by their very nature, have fairly good gamma ray detection efficiency. But of course, there's a limit to this. If you make them very, very small, they could be very efficient. However, the resulting recoil protons that you get from like Compton scattering with, for example, within the crystals, these recoil electrons could just end up, making their way through the crystal and leave the volume before they're able to deposit most of their energy. So oftentimes, that's why a very large inorganic scintillator is often desired, since you're able to get the majority of your energy deposited from your events in that case. Of course, there's other quote unquote disadvantages with using inorganic scintillators. One of them being that they tend to be hygroscopic. So you need to basically prevent any kind of contact with water with them, or just in general with the environment. So that's why you see, for example, in this middle picture, a lot of these end up being permanently sealed within a particular encasing, such that it's essentially enclosed or cut off from the environment. And this is just to retain the integrity of the crystals to make sure that they don't degrade over time or from exposure to the elements. So inorganic crystals are a very broad range in general. There's a lot of different type of materials that could be used for this process. And as a result, you end up having a bunch of, just in general, a bunch of different crystals that could be used. So I already mentioned before, sodium iodide tends to be a lot of the a very popular one in so much as that it has a very long history of production. So in terms of manufacturing costs, it's fairly cheap, and you can grow it to very, very large size, which at the end of the day, if all you want is very high efficiency, just having large volumes would be a reason enough to use that particular type of scintillator. However, there's other types. In this case, at the very bottom, we have cesium iodide. It's similar to sodium iodide. However, it has some physical properties that can make it more appealing, such as the fact that it's less hygroscopic and isn't as susceptible as the sodium iodide. However, the downside is, and you'll actually see this with a lot of more weird or out there inorganics, is because there's a very low demand, they aren't very much commonly manufactured, or there isn't that big of a supply. So they tend to be fairly expensive a lot of the time, depending on what you're looking for. Again, here's a even more example of different types of inorganic crystals that could be used. And here's even an example of a particular application. So one of them being over at CERN, they tend to use some of these types of inorganic crystals with their particular experiments. Again, so some of these are just for your note. I won't specifically go into very high detail on each individual one, but just note that the field of just scintillator detectors in general is quite vast and very expansive. So even if your research is specifically on, say, scintillators specifically, it'll be very rare that you have complete and utter knowledge of everything that's going on with scintillators in general. The field is ever so much advancing and having new and pretty cool research and developments happening. So I will point out though, here I'll just give another brief discussion on the way that a lot of these inorganic crystals are manufactured. So essentially, the process starts within a vat, and you have a seed, if you will. Usually in manufacturing, the seed serves as like the nucleation site from where the crystal will be growing from, and it tends to work best if that seed is just a small piece or like a small chip of the crystal you're actually trying to grow. That tends to end up helping. And there's a lot of different crystal growing processes. A lot of them are very similar, but could end up just having the crystal grow in a very different orientation or kind of structure. But needless to say, regardless of the crystal growing method that you go with, as a general rule of thumb, they tend to be very slow and get even slower as you try to go larger and larger in volume, which is why I mentioned before, especially with inorganics, you tend to not have many that are very, very large in volume or in size. And because a lot of these, like I said, tend to be hygroscopic, you tend to keep them encapsulated or enclosed in a particular kind of capsule. But you can also, a neat thing when you encapsulate them is you can also include a lot of reflective coating during this encapsulation. This helps a lot with the light collection process, because that way any kind of photons that are emitted during the scintillation process just end up reflecting from the sides and ultimately making it to the window, which is coupled to this, to the right is the PMT, and this is what's actually attached to this transparent window. And that's how you're actually able to ultimately extract your signal from your events. So here's just a general application. Say you have a gamma emitting sample, you have this sodium iodide PMT coupled setup, you apply a high voltage to power the PMT, and you're able to digitize the pulses. And what you're able to get is a plot resembling the red distribution here shown on the right. The red is the gamma ray spectrum that you would get using sodium iodide, measuring in this case cobalt-60. That's why you get these two peaks, one at 1.17 MeV and the other one at 1.33 MeV. You can see though that there's these this blue distribution also has these peaks at those locations, but are much, much thinner and much more well-defined. These come from another detector. It's called an HPGE, and it's essentially the gold standard in terms of gamma imaging. And I think I'll cover this. I should cover this a bit in one more future slide, but just for now, as a tease, yes, HPGEs tend to be the best type of gamma ray detectors to use, under the caveat that cost isn't an issue, because spoiler, HPGEs tend to be ridiculously expensive and also take a lot of accompanying equipment. You need to keep these really cooled down to very low temperatures, which requires additional equipment to do so. But anyways, finally, we have organic simulators, which are similar to the inorganics that we just talked about. The main difference being, as I mentioned before, they're primarily composed of hydrogen and carbon. And this mechanism of scintillation essentially boils down to the fact that it's still this fluorescent, you still have this fluorescence property where, as you have incident, say gamma rays that recoil off electrons, these electrons travel through the scintillator and excite some of the atoms in the that make up the molecules that make up the scintillator, and you end up with these very high density regions of singlet states and triplet states, where these states eventually de-excite via this fluorescence process, which ultimately gives off the photons that we end up collecting. Now, I can talk a bit more about the specifics of these different states, but for now, let's just worry about the prompt fluorescence, which is the main signal that would be of interest under most applications. And that would be collected, say, by a PMT, which you can, again, digitize into a pulse and collect a wave. Now, it's important to note that with organic scintillators, since they're low density, low Z, they may not always be the best for gamma ray detection because of their low efficiency. However, they have this neat property where their shape of the pulse is actually dependent on the initial radiation type due to this singlet and triplet state process, where essentially the delayed response or the tail of the signal is much greater for events that were initiated from a neutron scatter than from, say, a gamma ray scatter. And if you were to plot, say, the ratio of this tail region versus the total integral of your pulse, we call that pulse shape discrimination. And if you were to plot that versus energy or light, then you get this kind of distribution where you have these two different bands, where events corresponding to this top band are neutron events, and events corresponding to this bottom band are gamma ray events. So that's a really neat aspect of these organic simulators, which would be very helpful for particle discrimination under most applications. So in brief, we have a lot of organic simulator types. We have plastics, liquids, and organic crystals. They all differ in terms of some of their scintillation properties, but generally speaking, some of them are better suited for particular applications or scenarios, or where certain physical properties are more important to the actual performance. For example, like in cases where you need a high amount of efficiency, well, due to the inherent low density nature of organic simulators, you need something with a large volume to make up for that. As such, you would use plastics, since these could be made in a very large and huge quantities. So you would overcome the efficiency issue by just having a very large plastic simulator be used. Now, finally, there's a very important aspect with regards to gamma ray detectors, which is the energy resolution, which is the capacity of a detector to distinguish the interactions of different energies. And the way that the detectors convert, the initial energy deposition to a signal is sufficiently different that different amounts of energy deposition is used to create the carrier for the ultimately for the signal event. What I mean by this is with a scintillator, you have photons, which then are converted to photoelectrons. And as a general rule of thumb, anywhere from between 20 to 50 electron volts are needed to make one photoelectron. With gas, you only need 30 electron volts to make one electron ion pair. And with a semiconductor, it's in order of magnitude better, where you really only need 3 to 10 electron volts to create one electron hole pair. And with more of these pairs, or in this case, photoelectrons, you get a lot more statistics or a lot more photons created, say with a scintillator, for example, and that results in better resolution. If you were to characterize or histogram the peaks on a distribution, you would kind of end up seeing this kind of bell-shaped curve or peak, if you will. And if you take the full width half max, which is the value of this distribution at half the maxima, take this distance, that's a good indicator essentially of the energy resolution. It's often noted as the energy deposition over the, no, it's the full width half max over the energy deposition, where you want a smaller resolution, which corresponds to very thin peaks, which ends up making it a lot easier to identify different energies, especially if they're very close together. So here's an example of two different detectors, one of them with a moderate energy resolution, which is why you get this peak that's a bit wider. Meanwhile, you have that HVGE detector, which I mentioned was one of the semiconductor detectors that is ideal. It's the gold standard. It's the gold standard because it has among the best energy resolutions that you can reasonably achieve. And that's why this peak is much more well contained within its particular bin, if you will. And because of the fact that semiconductors need so little electron volts per electron pair, even a small energy deposition event could end up generating a lot of these electron hole pairs, which means you're able to get a lot better statistics and end up having these kinds of thinner peaks, which is why resolution is considerably better for semiconductors. In general, it's not always the case under certain circumstances, but for the most part, you can say that as a class, semiconductors end up performing the best in terms of energy resolution. And to further iterate that, here's again a comparison between an inorganic scintillator, in this case sodium iodide, and an HVGE detector, which is a semiconductor, and you can very clearly see how different the peak and the energy resolution is between these two systems. And then final remarks, since I think we're close to being done with with the time. So when choosing a gamma detector, there's a lot of things to consider. Of course, there's the application that you're going to be using such system. There's going to be the characteristics of the source that you may be dealing with. What kind of energy is it? What kind of activity are you dealing with? Where is it going to be? The geometry is super, super important. The location of the source ends up ultimately deciding a lot, especially in terms of how much count you're actually getting for a particular measurement. And of course, the detector material itself will end up having a good significant factor in terms of, what kind of decay times do you need to deal with? How fast a response do you need? How good of an efficiency do you need, et cetera, et cetera. And there's just a bunch of, a lot of other factors to consider where ultimately different projects end up finding needs for different type of gamma ray detectors, which is why ultimately there's been just so many types developed over the years. And now finally, to wrap everything up, as I mentioned before at the very beginning, we started with the Greeks and we'll end with the Greeks. Here we have Plato and Aristotle and the School of Athens. And I wanted to include this at the very end because, so we know that these folks are very famous philosophers, and they're known for their vast knowledge. And over the course of this presentation, a lot of this comes from a very important book, which here at Michigan, the nuclear engineering department, if you ever end up studying here, you'll be very familiar with this particular book. It is the Radiation Detection and Measurement textbook written by Glenn Knoll, plug-in for the University of Michigan there. But essentially, it serves as the Bible for radiation detection and measurement knowledge. So if there's anything in this lecture that you want to know in more detail, there's like a 99% chance that you'll end up finding it in this textbook and it being covered in a much deeper and more intricate detail than what I was able to do here today. But either way, thank you. I'll just finish off by saying fair use disclaimer, bibliography for some of the references used in this presentation, and image references. And again, I'd like to thank you all for your attention for today's lecture. Thank you.
Great work, Ricardo. Yeah, thank you. Do we want to take questions? It is after 2 at this point, so we are technically past.
Yeah, so officially the lecture's over, so you're all free to leave, but I still have time, so I'd be happy to go over the questions with you all if you want.
Sure, so we'll go through a couple of these then. We'll probably try to limit it to 1 per person just so that we can get through everything. William Redding asks, since we're not measuring neutrons or gamma rays directly, do we record ionizations instead of neutron or gamma flux?
Right, so you can still get the neutron and gamma flux basically based on what you end up measuring. So there's it's very complex and it really depends on your particular measurements and setup, but you are definitely able to still using certain calculations or certain equations, be able to basically back calculate what the incident, for example, what the incident photon flux would be on your detector based on your response. Thank you. Good question.
Yeah, and Dile Nema says, does a TLD only measure gamma radiation exposure, or does it also protect radiation workers from the exposure too?
Right. So good question. So this might be a misconception that a lot of folks have with dosimetry, but the dosimetry itself doesn't protect you per se. It doesn't do anything to keep you safe. It's literally there as a method of monitoring and keeping track of your exposure over a certain period of time. So unfortunately, in the case, say, of an accident or an accidental exposure, it's not really going to do anything in terms of helping you with that, but it will at the very least be able to tell you how much you were exposed to from that particular event. And knowing how much dose like a person received would be very important to know in terms of diagnosing, what would be the best procedure, what would be the best steps to do in terms of make sure that the patient ends up being all right.
Abhishek Pende wants to know, does Raman scattering take place while interactions of gamma rays?
All right, so that's one of like the more exotic, if you will, gamma ray radiation types, which unfortunately, just based on my research and what I've been able to learn through my courses, I've either at this point really forgotten much about that, or it never really come across, because like I mentioned before, a lot of these particular gamma ray interactions are very, very specialized and only really come up with their particular field. And just unfortunately, with at least my experience, I haven't really been able to come across that. So unfortunately, I don't really think I have a good answer to that.
James Kiro Neritu asks, is there a relationship between the absorption coefficient and absorption cross-section?
Yeah, so if you recall from the presentation yesterday, there is an expression. Don't quote me on this, but I believe it's just the might be the reciprocal, but no, yes, they are intrinsically linked.
Yeah, sorry, I cut out there for a sec. Eric Chandler asks, is the white line on slide 30 the decision boundary?
Let's see, slide 30. Yes. So I didn't note this, but yes, that white line that you see there would be what we would call the discrimination line. It looks like a line because essentially what you do is you can take horizontal slices of this PSD plot and then create a histogram of the events. And if you were to plot this on a 2D histogram, you would see basically two Gaussian shapes. And what you can do is find the centers of those two distributions. One of the distributions being the ones that correspond to the neutron events. One of the distributions correspond to the gamma ray events. You can find their means and then figure out their sigmas via fitting. So you figure out their standard deviations. And now the discrimination value is, I wouldn't say arbitrary. There's a very good reason why certain groups use the value that they do. However, the discrimination value chosen could be basically up to the user. For example, in our case, and for the example for this part right here, the discrimination line was decided by finding the mean of the photon distribution and then going up 3 standard deviations above. That way, anything above that threshold or that value is statistically speaking very likely to be a neutron event rather than a photon event. And if you do this for a lot of slices across an energy range, you can basically then fit a line. It could either be a polynomial or it could be a power function fit, but essentially you can get this polynomial that can serve as your discrimination function. Therefore, all you essentially do is plug in an energy value, and then that'll give you a particular discrimination value for that energy. And if your PSD ratio falls below or above that value, it can allow you to do the particle discrimination. So yes, good question.
Yeah, figure of merit stuff. Love calculating that. It's always really
Yeah.
fun.
Yes.
Amir Bashir wants to know what properties of semiconductors contribute the most to their energy resolution.
So I mentioned this before, but it basically just has to do with, statistically speaking, has to do with the fact that you get a lot of information carriers, of what we would call them in general, but you get a lot of electron hole pairs per incident event. And because of the way the statistics work out, you end up being very certain then in that particular event's energy deposition. That's mathematically speaking why, I don't know, do you actually, Peter, do you want to comment on that? Do you have anything to add with regards to that? Because at least with
a lot of
mine,
it has to do with a lot of it has to do with electron and hole mobilities in the detector. It has to do with like perhaps trapping and recombination sites that we consider in the detector themselves. Sometimes it has to do also with like the anode and cathode design as well. Whether there's a Frisch grid in there, and if you don't know what a Frisch grid is, I'm sure someone will talk about it eventually. Whether or not there's like a coplanar grid, for example. There's a lot of both intrinsic material properties as well as like extrinsic anode and cathode design properties that allow for semiconductors to get really high resolution energy measurements. And it mainly has to do with electron hole pairs. Going on, Johnson Maseko asks, what are new gamma detectors for a nuclear power plant can you recommend as best in market currently?
Okay, well, that's fairly easy. So if you were not constrained with costs and you were not constrained with space, i.e. auxiliary equipment, then it would 100% be just to equip your facility with as many HPGE detectors as you could. However, for a lot of facilities, it's just simply not feasible because of the fact that typically HPGEs need a lot of maintenance and to make sure that they're properly calibrated and to make sure that they're performing as intended. I mentioned before, basically with HPGEs, in order for them to be working properly and to get the actual energy resolution that you need, they need to be super cooled down to very, very low temperatures. Oftentimes, this is either done via electrical cooling, so they take up a lot of power, and because you need these systems to be portable, they basically use portable batteries, and you can only get so much charge on them that eventually you need to recharge them. So in terms of how much can they go being used without being charged, it's not super long if they're mechanically cooled. but then there's the ones that are cooled with just liquid nitrogen, like dewars or canisters. And now those don't have the limit of, running out of charge or electric charge for power, but you still run into the issue of that those systems tend to be very bulky and not very mobile because of all the additional cooling equipment you need to do. So that's an issue. And then of course there's costs, like HPG detectors are by no means very cheap. So if you want to, for a particular reactor facility, it may not be the best option to, to go with that, which is why what's typically used in the field are a lot of sodium iodide based ones. You can look up Fluke is a very popular like portable handheld gamma ray detector. That's that the company supplies a lot of portable handheld detectors that are used out in the field for various scenarios. And some of their models also include small helium tubes for neutron detector to disarm capabilities, but mostly for gamma rays. So I would say very common to have like several sodium iodide detectors, for example, and then have like one or two HPGEs when you need to have really, really good characterization for like a particular, case or something.
All right. And the last question we have from Stephen Bryant. You used a reference from ENDF. What does ENDF mean? And do you have a lot of to-go-to references when you do work with gamma detection?
Okay, nice, great question. So I can definitely, so to answer the last bit of the question, as you do have a lot of references, over time you just end up accumulating a lot of papers and textbooks. But I would say when you're like starting off with, I cannot recommend the NOAA textbook any more than I already have. It's basically your go-to for most stuff or most questions that you have. And if it doesn't, directly answer whatever kind of thing you're looking for, chances are it references something that you can use to ultimately get to the answer that you're looking for at the end of the day. As for NDEF, off the top of my head, I don't recall the abbreviation, but essentially it's the database for a lot of the it's a nuclear database that has a lot of the cross-sectional information for basically all of the isotopes that are fairly well characterized over the past couple decades and everything. It's continuously updated. So whenever new, fundamental nuclear science experiments perform cross-sectional studies, their results eventually end up making it to that database eventually to keep, everything current and with the smallest degree of uncertainty that we have.
Yeah, ENDF stands for Evaluated Nuclear Data File. I pulled up the website. It's super easy to find. If you just Google ENDF and look for nuclear topics, that's where it is. It looks like that's all the Q&A here today. So for those of you tuning in, thank you so much for your continued attention and participation. Make sure that you follow the details that Courtney put in the chat if you haven't already, assuming you can see that. If you can't, attendance is collected automatically when you log in. So make sure you just use the same email address and name you registered with so we can track your attendance. If you logged in with a different account, just email Courtney at cwagoner@umich.edu. That's CWAGONER@UMICH.edu so that you can get that registration attendance all taken care of. That's it for today. Tomorrow it's going to be alternative materials, I believe, some thallium bromide detectors by Eric Hall. So tune into that. That'll be really exciting. You can learn about the new stuff, the new radiation detectors that are currently being developed. It's the really cool stuff. So yeah, thank you again for your attendance. Thank you, Ricardo, for an excellent lecture. And we'll see you around.
Sounds good.